I created a schematic of the HV supply and added some of the things that I didn't have on the original schematic. That includes an approximation or an estimation of what the final stages of the photo of the multiplier section of the HV supply would look like on the top part over here. That includes the diode capacitor network, and I put in 3 stages here just for illustration, and that is driven by the so-called flyback transformer, although I wouldn't call it a flyback transformer. It would probably be just a regular step-up transformer, and that is driven by this 50 volt internal DC supply created in the machine, which is driven to the center tap of the primary. I measured the inductance of the primary and I found that to be 175 microhenry, and I built this transformer without knowing, of course, the secondary side. I just assumed some gain or some step up ratio here. The primary side is then driven by the two drivers, 2 NPN driver transistors, which are in this case shown as 4 devices in parallel, with the base resistance which is controlled by the HV control board, which I will show once I pan down this schematic. And the load is basically, in this particular example, I put in a 100 kilo ohm load on the output. And what I'm simulating here is a output of about 100 volts, and I built a feedback network to regulate this voltage to 100 volts. And I'll show the results of that after this schematic presentation. I did change the bias network a little bit to add a DC bias for these NPNs. Otherwise, in the original schematic, I wasn't able to get these NPN transistors to turn on with just an AC coupled driver here. Perhaps someone can comment on how this would actually work without a DC bias here. So I will now pan down to show you the actual control part, which is actually in the schematic which I showed earlier, but I did modify, or actually had to create a circuit for the AGC or the OTA based stage that was missing in this original schematic. Now this is the lower portion of the schematic, simulation schematic that I have. The whole section over here is almost the same as the one in the schematic I had shown in my last video. On the left side is the oscillator, which is relaxation oscillator, which is which is actually using this IC, very similar to the one in the actual machine. I tuned the frequency to get roughly what I was seeing in my machine, about 18 kilohertz. That square wave is AC coupled and fed into this OTA, which has a adjustable current source. So as the current is changed in this tail current source here, the overall voltage that is created across these two resistors changes. As you increase this current, the swing across the output, differential output over here, will change and increase. And using that feedback from the HV supply, which is the output of the HV supply after dividing down by a 1:100 here, I feed it into this error amplifier, which is basically a comparator. The set voltage is 1 in this case, which results in an output voltage of 101 volts based on the dividers that I have here. The output of this amplifier is driven through an effective resistance, which converts the voltage into a current drive into this base of this OTA's tail current source. When the loop is settled, these two voltages at the input of this OTA, of this amplifier, actually will become equal, and the output of this will essentially start to flip back and forth from on to off rapidly depending on the current load and dynamic conditions of the load. And this transistor will essentially turn on and off depending on again how quickly the load is being discharged or any other transient effects that may be going on at the output of the HV supply. The output of this OTA is then driven into this two of these driver stages. One is the positive drive and one is the negative drive. And this has again internal gain, AC coupled again between the OTA to this driver stage. The two outputs are then of this driver then feed the base of this NPN transistor, 4 NPN transistors, and similarly for the negative side you have the negative drive going into the 4 NPN transistors. So this essentially mimics the overall voltage control loop of the HV supply, and the part over here that I've shown in the feedback network to control the error amplifier is my own guess as to what would be happening, and I just did it so that I could see how the loop would settle and converge. Next I will show some simulations of what I've done using this schematic. Now here's the simulation of this whole loop starting from time equal to 0 as the power supply is turned on, and I'm going to show 4 of the nodes that I plotted here. I'm basically looking at the schematic. The first node is the current into this OTA, which is your basically your voltage control gain of this whole loop. The number 2 is the AGC voltage, which is driven by the error amplifier. Node number 3 is the base voltage of both of these transistors, and finally the last one is the output of the HV supply right over here, driving the 100k load and the voltage divider. This is a 1 leg in series with a 10 kilo ohm resistor, and I've tapped off on the 10k side to reduce the voltage by approximately 100 times. So looking at the top schematic, initially when the HV supply is powered up, the error amplifier is fully driven to try and maximize the output voltage to bring it close to the target voltage of 101 volts. So at this point it's each of the transistors, there are 4 of them, has a current of about 80 microamps or so, as you can see here. And once it's settled, it starts to basically just toggle depending on the load condition. If there is any kind of a discharge or as the load changes, and it's highly dynamic circuit with a lot of feedback and I'm sure some noise as well, so it causes some of these transitions to occur in the steady state. The AGC voltage, as you can see, is pegged here. That is the divided down version of the error amplifier, which would of course rail to 12 volts, but in this case I'm reducing that amplitude of the current that can be driven into the base by using the resistor network. And again, it's basically pegged all the way until it reaches almost a steady state, and then it starts to toggle again, which is exactly what the bias current would look like going into the transistor. And VB1 and VB2 are the switching voltages that are being driven into the base of the final output devices, which is then amplified in the transistor to create the large current that used to charge the multiplier part of the HV supply. And this is the actual output voltage. You can see in this particular case, actually starting off I didn't start from 0, but this is actually time shifted, so starting at 69 volts and going up to the 101 volts right here, at which point the loop is stable and the voltage is maintained within a certain small range around 101 volts. Next I'll show a little bit zoom in of the whole thing, and just to show the zoom in part of the settled portion here. Now this is the zoomed in portion after about 200 milliseconds of simulation. In this case, I'm only again showing the latter part of the simulation to show the settled portion. The top here again is the current through the bias transistor in the OTA on the AGC stage. And this is the output of the AGC voltage, AGC stage voltage, which is VAGC, and again this is about 0.7 volts swing. This is the voltage on the bias of the transistor, and finally the output voltage at the HV supply, which is 101 volts, and the actual value of the average of this 100 milliseconds worth of time is 100.976 volts, or an error of 0.024%. Now these spikes can be reduced by changing some of the driving currents. If it's reduced a little bit, the overall amplitude swings will be less, but might be a little bit more sluggish. So it's basically, I'm not trying to mimic the exact behavior in terms of the AC dynamics of this supply. I'm just trying to get a rough idea as to how this overall circuit works. In the actual device, when the HV supply is higher than the set voltage, this entire loop turns off, as you can see in the measurements or in the lab experiments I did. And basically these voltages will be quiet until the HV voltage falls below the set point at which the loop re-engages and starts turning on the driving transistors.